All right, so tonight's topic is going to pick up where we left off after our last class. We talked about encoding binary numbers, usually whole numbers, right? So now we're going to take one step further and introduce the concept of integers. So integers are different from whole numbers in the sense that it represents the concepts of positive numbers and negative numbers. So very important to note that for purpose of storing the positive or negative, there's actually no sign that representation hardware. So there's no dedicated hardware that says this is positive or negative. So you have to come with some way of representing the value positive or negative. So here are four methods or encoding schemes we're going to look at tonight for encoding the concept of negatives into binary. So let's start with the first one. With sign magnitude, the encoding, the leftmost bit or the highest order bit is going to be reserved for the sign bit. So 0 will represent positive numbers and the value 1 will represent negative numbers. So the rest of the number or the rest of the bits in the number are going to be reserved for the magnitude. So the magnitude is another way of saying absolute value, right? So we have two examples down there at the bottom of the screen. You have positive 5 and negative 5. So if we look at positive 5, positive is represented with a 0. I'm going to now highlight this so you can see. So have positive, right? The leftmost bit, 0 set to positive, and then 101 for 5. To make it negative 5, you have 1 for negative and then 101 for 5. Okay, so positive 5 and negative 5, very straightforward. So some issues with using sign magnitude is that we have this. You have positive 0 would be 0, 0, 0, 0, and negative 0 would be, right? So based on the definitions that we provided, sign magnitude looks like it represents 0 if both positive and a negative 0. But if you have used integers in math, you notice that there's no such thing as positive and negative 0, right? You have positive 1 and negative 1, but there's just should only be 1 0. So that's one issue with sign magnitude, is that you have two representations for 0. And the number of bits is, again, very important. Let's say I have three bits, right? So if it's unsigned, the smallest number is 0, and the largest number is 7, right? If this is unsigned. Now using sign magnitude, the smallest number is still 0, right? Now, but the largest positive number is 0, 1, 1, right? Because this is a sign bit. So this is positive 3. So very important is that even though I'm using the same number of bits, the leftmost bit is reserved for sign. So I can't use it to represent the magnitude. So the range of numbers that are represented using sign magnitude, you're losing one bit because instead of allocating all the bits to the magnitude, one of them is reserved for sign. Okay. All right. So let's take a look at the next thing under sign magnitude is that we have an exercise here. So given these two numbers, 0, 1, 0, 0 and 1, 0, 1, 1, I want you to spend a minute, convert them to decimal. Tell me what the corresponding decimal integer is. Okay. Give you like a minute or two to work on this. Okay, so let's do this one together. So the first number, 0, change the ink, 0, 1, 0, 0. This is a sign bit, so it's positive. And this is a magnitude, 1, 0, 0 is 4. That's positive 4. Second number below it, 1, 0, 1, 1. This is negative, right? And then this is going to be 3. So the top number is positive 4. The bottom is negative 3. Okay? All right, let's go to the next slide. All right, so now we'll go the opposite direction. Now you are given a decimal number, 2 decimal numbers. You want to convert your sign magnitude. So remember, when you convert your sign magnitude, it's just the first bit is going to be the sign and the rest of it will be the actual number. Okay, so to make it clear, I want you to convert this to 4, do 4 bits. Okay, so convert it to a 4-bit number. All right, give you a minute to work on this. Okay, so let's do this. We have the first is positive 3. This is 0, and 3 would be 0, 1, 1. Okay, so that makes it 4 bits. The next one, negative 2, we have the sign bit was 1, and then 2 would be 0, 1, 0. All right, and that would be negative 2. All right, hopefully everyone got this. So now what I would like you to do is we're going to do an exercise and fill out this whole chart for this class. So let's start off with binary. You have these 8 binary values, right? Or binary numbers, I should say. So we're asking is, what would be the decimal value of this binary if the encoding was unsigned? So for example, 0, 1, 1, if it's unsigned, this would be 3, right? And if sign magnitude was used, 0, 1, 1 would be positive, because it starts off with a 0 at the beginning, so it's positive, and then the value would still be 3. Okay? So what I want you to do is fill out these 2 columns. So give you like 2 or 3 minutes to do this. So do this, fill it in, and we'll see that, hey, sometimes it's the same, sometimes it's different. All right? Have at it. Okay, so let's do this together. All right, so this, if it's on 0, 1, 0, if it's unsigned, we would have the value 2. This would be 1. This would be 0. This would be 4, 5, 6, and 7. Okay, so the first column should be a review from our last class. So now it's sign magnitude, we're going to see that this is positive 2. This is positive 1. This is now positive 0. This would be negative 0. This would be negative 1. This is negative 2. And this is negative 3. Okay, so notice when it's positive, essentially it's the same value. You have a sign bit in front, but essentially it's the same value. But when it's negative, obviously unsigned has no negative. So that's why you have 4, 5, 6, and 7. But when it's signed, half of the numbers are positive, the other half are negative. Okay, so let's go one step further. Let's take a look at another encoding scheme, 1's complement. So 1's complement is similar to sign magnitude in that you have a sign bit, 0 is positive, 1 is negative. That hasn't changed. The remaining bits are the magnitude. That's also just the same. Now, if the value is positive, then it's actually the same as sign magnitude. Virtually the same, no changes. The difference is when the value is negative. So if the value is negative, then the magnitude bits are complemented or flipped. All right, so what does that mean? So let's look at this example here. Positive 5, 0 for positive and 5, right? So remember we said that when it's positive, it's just like sign magnitude. That's why 5 and sign magnitude and 1's complement look the same. However, when it's negative, look at the bits. You have your sign bit from 0 change to 1, right? And then your magnitude 1, 0, 1 change to 0, 1, 0. So every bit is flipped. So positive 5 and negative 5 looks like the mirror image of each other, right? Or the opposite. So if we look at that, even without knowing that the top number is positive 5, we just look at the bits at the bottom and we know the relationship between these two numbers is that one is the negative version of the other. Okay, so that's 1's complement. So essentially when it's positive, it's all the same, but when it's negative, all the bits are flipped. So now let's take a look at this exercise. All right, so give you a minute. I want you guys to do this. So assuming now that you have two numbers, 0, 1, 0, 0 and 1, 0, 1, 1, I want you to convert to decimal, knowing that I want you to convert it, that these are 1's complement numbers, you're converting to decimal. Okay, give you a minute to work on this. Okay, let's work on this together. So the first number, 0, 1, 0, 0, sign bit is positive, and the remaining 1, 0, 0 is just 4. Okay. Now the second number, 1, 0, 1, 1, the sign bit is negative. So because it's negative, the magnitude bits need to be flipped to get the value. So this is 1, 0, 0, and that's 4. Okay. So we have +4 and -4. Any questions? All right, next. Okay, so now we start off with the decimal value. So +3 and -2. Give you a minute, convert these to one's complement following the rules that we've discussed. Okay, so let's do this together. So +3, this would be 0 for the sign, and then the magnitude would just be 3, 0, 1, 1. Okay, so again, when it's positive, it's just like sign magnitude. Now for -2, because it's negative, sign bit is 1, and now we start by converting 2 to 1, 0. 0, 1, 0 would be its binary. Now, because it's negative, I need to flip it. So this becomes 1, 0, 1. Okay, so those are my two binaries for +3 and -2 in one's complement. Okay, so if there's no questions, then I want you to spend a minute or two, fill out this column now, one's complement. Assuming that these binary numbers are encoded in one's complement, what is the value stored if this one's complement was used?
Professor, I have a question.
Yes.
Why is it called one's complement?
Complement meaning that complement, when the word complement means it's the exact opposite, right? Or for exact complementary. So you have if you have 0, its complement is 1, is the other half of it. So you start with complement. Now why use ones? I'm not quite sure, because I think once you have 2s, it just increases. There's an increment. So I suspect it has to do with the fact that if this was the only encoding, then it probably wouldn't be called one's complement. It's the fact that you have something else afterwards. So that's why they started with 1s and made it 2s, because that allows you to show that there's comparison between the two. Okay, but the word complement means the opposite of the value. So instead of just 0, the complement of 0 would be 1. So hence the word complement in there. All right, hopefully that's a sufficient answer for now.
Okay, thank you. Yeah, it was. Appreciate it.
Okay. Okay, so let's do this together. One's complement, when it's positive, it's the same. So this is +3, +2, +1, and +0. Now, when it's negative, it's going to be different because you have to flip the bits, right? So this is negative, and then these two digits, 0, 0, that becomes 1, 1. So 1, 1 is 3. This is negative, and then we have 0, 1. So 0, 1, you flip it, becomes 1, 0. 1, 0 is 2. This one, you have 1, 0, you flip it, becomes 0, 1. So that's 1. And the last one, the last two bits are 1, 1, so you flip it, it becomes 0. Okay, so that's one's complement. So when you compare one's complement to sign magnitude, they essentially represent the same range of numbers. You're not getting more numbers. If you look at this chart, you have +3 and -3. And when it's positive, it's the same, but really comes down to it is when it's negative, it's different. So what makes it different is that the bits are flipped so that its relationship to the positive number is the exact opposite. Okay, so it's just a little more intuitive. Now, however, there's one big problem, especially when it comes to math. I mentioned earlier that when we do integers, you have +3, +2, +1, and then it's 0 and then -1. There's no +0 and -0, right? Because they should all both be 0. So 0 really doesn't have a sign. So this creates an issue here where if you're trying to do math, math doesn't work really great when you have two representations for the exact same value, right? So that's what 2's complement tries to address and to get rid of that extra 0. And how does it do it? Well, let's look at the specs. With 2's complement, the leftmost bit is a sign bit. So that's just the same as before. The remaining bits are the magnitude. That's the same as before. So if it's positive, it's the same as one's complement and sign magnitude. So the difference really is if it's negative, then the magnitude bits are complemented just like one's complement, but you need to have this one extra step, which is add 1. Okay, so when the value is negative, you have to not just flip the bits, but you have to add 1 to the magnitude. So not to the whole number, add 1 just to the magnitude. All right, so let's see in practice. So in this example, I have +5, which is 0 for positive and 101 for 5, right? So how do I go from +5 to -5? So what happens is I flip the bits, right? This is now 0 becomes 1 for negative. And then 1, 0, 1 gets flipped into 0, 1, 0, right? So 0, 1, 0, I add 1 to it. So 0, 1, 0 is 2. I add 1 to it, becomes 3, so it becomes 0, 1, 1. So that's what I have over here. Okay, so when it's negative, you take the bits, magnitude bits, flip it, and always add a 1 to the magnitude. All right, let's see the exercise. All right, so with that being said, I want you to look at these two problems again, 0, 1, 0, 0 and 1, 0, 1, 1. I want you to convert it to a decimal value. So remember, you convert the magnitude and then you add 1 to the magnitude. Okay, so give you a minute or two to work on this. Okay, so let's do this. So the positive number is straightforward. 0, 1, 0, 0, just like before. This is positive, and this would be 4. So when it's negative, that's where it gets there's a little more work involved. So this means it's negative, and because it's negative, you need to flip these bits. So this becomes 1, 0, 0, and then 1, 0, 0 plus 1 is 1, 0, 1. So 1, 0, 1 is 5. Okay, so it's positive 4 and negative 5. Okay, so now I want you to take these two decimals and convert them to 2's complement. Okay, so remember again, when it's negative, you flip the bits and add 1. All right, let's do this. Okay, so let's do this. Positive 3, 0, and 3 is 0, 1, 1. Negative 2, 1 for negative. Now 2 becomes 0, 1, 0, but I have to flip the bits, so it becomes 0, 1. Oh, I'm sorry, not 0. Let me erase that. It's 1, 0, 1. And I add 1 to it, so it becomes 1, 1, 0. Okay, so positive 3 and negative 2. All right, so if there's no questions on that, let's fill in this column, 2's complement. So now assuming that this is your binary and is encoded in 2's complement, what would be the corresponding number value that is represented? Okay, so let's do this together. All right, this is +3. This is +2, +1, and this is +0, right? So now I'm going to start from the bottom for a reason. Let's start with 1, 1, 1. The sign bit is 1, so I know it's negative. And then the magnitude is 1, 1, right? So I flip the bits. 1, 1 becomes 0, 0. So 0, 0 plus 1 is 1. Okay. This is negative. And the magnitude here is 1, 0. I flip it because it's negative, so it becomes 0, 1. So 0, 1 is 1. 1 plus 1 is 2. All right. Now with this one, the magnitude is 0, 1. I need to flip it to 1, 0. So 1, 0 is 2. 2 plus 1 is 3. Okay. Now the very last one, negative. And then I have 0, 0. I flip the bits, becomes 1, 1. 1, 1 is 3. Plus 1 is 4. Now that's done. Compare 1's complement to 2's complement. Notice that when it's negative, Q's complement, you added an extra digit to it, right? Sort of what happens, you sort of shifted it. So notice that what's missing here is that in 2's complement, there's no -0 anymore because we incremented the magnitude. So now it shifted up. So compare 1's complement to 2's complement, it looks like every number is larger by 1, right? So what happened is now we have no zeros, so that's great. But now we have an extra digit, -4. All right, so that's another difference in 1's complement and 2's complement. I got rid of the -0, but now I get one extra negative number, -4, because everything was shifted up. Okay, so now if I look at this, I only have a single 0. I can choose to remove the sign, doesn't really matter, because now I can represent all the integers, +3, +2, +1, and then 0, -1, -2, -3. Okay, so 2's complement, because it gets rid of the 0, this is the default. If people don't say anything, generally speaking, 2's complement is used for arithmetic. So if you see addition, subtraction, multiplication, it's a safe bet it's using 2's complement, simply because of the fact that we can get rid of the 0. Okay. Now, those are the easy ones. Now comes what is a little more difficult. Excess K, or it's also called excess N, depending on where you read, but they both mean the same thing. So with excess K, there are no sign bits. So we don't allocate a single bit to the leftmost bit to say this is positive, this is negative. The way excess K works is that it's a binary encoding where 0 is mapped to the lowest minimal negative value. Okay, so what does that mean? That's like a mouthful. So let me tell you a little story. So this is a completely made up story, but it helps you understand the concept here. Okay, so pretend we're going through an imaginary world, and we say, okay, we're gonna invent Celsius temperature, right? We'll say, well, you know what? I'm gonna start with 0. 0 is freezing. H2O, 0 degrees. And then if I heat it up, once it gets to 100 degrees, water's boiled and it's gone. It turns to vapor, it's gone, right? So that seems like a very good scale where we have water that below 0, it turns solid. And between 0 to 100, it's liquid. And once it hits 100, it turns to gas, right? Perfect. And then we measured, freezing, saying, hey, it's solid, right? It's 0. And then we realized, wait a second, it actually gets colder. You can get below 0. So what's the lowest negative temperature that you can get in nature? Anybody? Anyone who's taken a science class. Could be physics. It can also be chemistry. What is the lowest temperature?
I think it was like 0 Kelvin.
Well, here, what's important is you need to pay attention. What's the temperature?
Oh, in Celsius, I'm sorry.
So what's the temperature though? You guys can look it up. This college class. So pretend we're sitting here talking. What's the lowest temperature they can get to? That it cannot get any lower. It's negative what?
People are saying negative 273.
Correct. Negative 273. And this temperature is called absolute zero, right? Because this is the lowest temperature that can exist in nature. It cannot get colder. Okay, so it seems like very awkward that, hey, you have a whole temperature scale here where the lowest number is negative 273. That seems a little arbitrary, right? Why not? But however, it is what it is because they created zero first. And then as they measured, they realized, oh, it can get colder, 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 until they realized 273 is actually the coldest. It's not zero. Okay, so that's where Kelvin comes in. Kelvin says, you know what? It's really silly to start, at negative 273. That seems so arbitrary. So if 273 or negative 273 is the very floor, it can't get any colder. How about we reset this to zero, saying that this is now our new zero. And that means freezing point of water is 273. And boiling point of water is 373. Okay? So does everyone see what happened here? Each degree of temperature is still incremented the same amount. The difference is instead of starting at negative 273 at the bottom, we're saying the floor is now zero. Does that make sense? So this is essentially what excess K does. Excess K means binary zero corresponds to negative K, whatever K is set to. All right. So for example, if I have excess 10, that means that binary zero, I'm just putting 3 zeros here, to decimal conversion, 0 corresponds to negative 10 because this is this number. Okay, so if I have excess, let's do another one, excess 100 to decimal conversion, that means that 0 under this format corresponds to negative 100. Okay, so that's what excess means. So whenever you use excess, whatever number, you are using an encoding scheme where you've defined the minimum number already. So there's no need to incorporate a sign bit because 0 corresponds to negative whatever the value is. Okay, does that make sense? All right, let's take a look at some back to the lecture notes and look at this exercise. Okay, so in this exercise, or actually example, you have excess 3, right? So with excess 3, notice that 0, binary 0, corresponds to negative 3. And then 1 corresponds to negative 2, 2 corresponds to negative 1, 3 corresponds to 0. So as it increases in number, the decimal increases as well. Okay, so this number can go to infinity, which means you can represent everything that can grow, infinitely. However, it cannot get any smaller. So you predefine what the base number is. So that's primarily what excess K does, is you predefine the minimum negative number. All right. Okay, so with that being said, let's create some exercises for you. So assume you're given a problem. You're given 1011 in excess 5, right? And we want to know convert it to decimal in base 10. How would you do something like this? So here's the method, or here's the strategy. Whenever you see an excess problem, you see it's excess 5, you create a chart, excess 5 to decimal conversion, right? You're gonna say 0 corresponds to -5. Okay. So now we want to know what 1011 corresponds to. Well, here's what we do. We convert these to decimal. So this is 0 coming in this direction. I'll change the ink color. Going in this direction is subtract 5, right? So up here, 1011 is binary for 11. So it's going to be 11 plus, oops, not plus, 11 minus 5, right? In this direction. So this is going to be 6. So that's the answer. All right, you figure out moving from left to right, you subtract 6 from it. All right, so give you a minute. I want you to work on one yourself. So give you this problem. Let's say you're given 1 0 1, and it's excess, let's say 7. I want you to tell me what the decimal value is. Okay, give you a minute to work on that. So you have 101 in excess 7. I want you to tell me what the decimal value is in coding. Okay, so let's do this. So we start off with excess 5 decimal. Okay, so we know that binary 0 corresponds to, I'm sorry, this is 7, -7. Okay, so going in this direction, it's subtract 7. So now I have 101, which is 5, right? So 5 going in this direction, I take 7 away from it, it becomes -2. All right, and there's your answer. So 101 in excess 7 is -2. All right, now let's assume that you're given something else, a different direction. Let's see, we have the number 6 in decimal, and you're asked to encode it into excess, let's do excess 6. Let's do, yeah, there you go. 6 and encode into excess 6. So how would we do that? Well, we would start with the same little chart here, right? 0 corresponds to -6. So now I have 6, I need to come in this direction. So to go into that direction, it's add 6, correct? So we have 6 plus 6 is 12. So I just need to encode 12 into binary. So 12 in binary is 1100. Okay, and this is your answer. All right, give you guys one more to do. Let's do 7 and encode it into excess 5. Okay, give you like 2 minutes to work on this. Okay, so let's do this together. So excess 5 to decimal conversion. 0 corresponds to -5. So I have 7. So moving in this direction, it's +5, right? So 7 plus 5 is 12. And now we end up with 1100 also. Okay, so notice that 1100, depending on which encoding, it can either be 5, it could be 6 or 7. So each excess number is a separate encoding, so they're different from each other. Okay. All right, so now with that done, let's just fill in the last column. So assuming that excess 5 is used for these numbers, tell me what the decimal value should be.
Professor, what are we assuming? Oh, never mind. Oh, excess 5. Okay, I got it.
Okay, so let's do this together. All right, so XS5 means that binary 0 corresponds to -5, right? So then we can just increment it. This is -4, this would be -3, and this would be -2, and 4 would be -1, and this would be 0, and this is 1, and this is 2. Okay, so did everyone get that? Okay, no one said anything, so I'm assuming you did. All right, so hopefully today, after tonight, you are now all familiar with at least these 4 encodings. So we went over these 4 representations of negative numbers because not so much sign magnitude, but the excess k, 2's complement, 1's complement, you will see them again because they're actually part of different types of mechanisms and specifications. Like for example, 2's complement is used in arithmetic a lot. Excess k is used as part of encoding for floating point numbers. And 1's complement is used for error checking when we do talk about data. Okay, so these are all encodings that you will see at one point or another, especially if you plan to have a career in computer science. Okay, with that being said, does anyone have any questions for tonight?
Professor,
Yes.
I wanted to speak to you after class, if that's okay.
Okay, that's fine. Just hang out after class. All right.
Professor, I
Anyone
have a
else?
question about 2's complement.
Okay. What's your question?
Wait, so to get 2's complement, you just go backwards, like you say.
Go backwards. Oh, okay.
Sorry, like when you're given a number in binary and you want to
Uh-huh.
solve, find out what it is in 2's complement, you want to find out what it is in decimal. You just
Well,
like
let's just go back to this slide. So which direction are we talking about? Going from binary to decimal or decimal to binary?
like you're
Which
going from binary to decimal.
Binary to decimal. Okay, like here. Okay. So we have these 2 examples. So we have 0, 1, 0, 0 and 1, 0, 1, 1. Okay, one's a positive number and one's a negative number.
Right. So you
Okay.
Okay, sorry.
No, just looking at this, first determine the sign, whether it's positive or negative. And if it's positive, you just need to convert the binary for, in this case, 1, 0, 0 is converted to 4 and you're done. However, if it's negative, you have to flip the bits and add 1 before you convert it.
Right, but then when earlier when you were going the other direction, you were
Other direction, so decimal to 2's complement then. Are we talking about this direction? Decimal to 2's complement?
yeah, it just seemed like in both directions you were flipping the bits and adding 1.
Yeah, that's true. Yep, it's always add 1.
Right, but it seems like you would, in one direction you would flip the bits, then add 1, and then in the other direction you would add subtract.
You would think so, right? But just remember, you flip the bits. So it's always adding 1. Trust me, it's always going to add 1.
Right, so it's just either direction you're going, you're flipping bits.
Correct. Less things for you to remember. So just remember, always flip the bit and add 1. You never subtract. It's always add.
Yeah, I just got confused because you're going the other way, so I thought you would subtract 1.
Yeah, I know it's not intuitive, but you're going to test it. You go, oh, he's right. You always do add 1.
You're right. All right, understood.
Okay.
Thank
All right, no problem. All right, guys. Good night. Have a good weekend. Today's it's Thursday already, right? Wow, how time has flown. Okay, so I will see you guys on following Tuesday. Have a good weekend. And for
sir.
whoever want to talk to me, stay in class, and we'll just hang out afterwards.
Thank you, Professor.
All right, thank you. Have a good night.
you, brother.
Professor?